Thank you. Hello everyone, I am Aurora Naska, and I will be presenting today a joint work with Cremers and Charlie Jacomme on formal analysis of session handling in secure messaging, lifting security from sessions to conversations. During this work, we actually look at the Signal protocol. As many of you may know, so Signal serves as a backbone of many secure messaging applications that we use, such as WhatsApp, Facebook Messenger, Skype, the Signal app itself, and so on. And in particular, during our work, we were interested in the post-compromise security, or PCS. Informally, PCS can be defined as the security of a conversation being restored after some healing period, even when all secrets of a party are compromised by an attacker. So if we look at the timeline of the attack, this means that if at some point the attacker knows all the secrets of a party, but then it allows during a healing period such that the parties can, the honest parties can introduce new cryptographic key material into their key derivation function, then once the attacker goes back online, there is a guarantee that future sessions or the future of the conversation is secure. For example, the attacker cannot introduce new messages in the conversation because the parties cannot decrypt those with the keys that they have. And this is studied extensively in the literature in the following setting. So there are two parties, Alice and Bob, which share a single session, meaning a single execution of the key agreement protocol, the X3DH, and then they use the double ratchet to exchange any number of messages between one another. But that's hardly the case in reality, because the parties have multiple devices and every device shares multiple sessions with other linked devices. And to add complexity to that, what happens is that these devices can also be temporarily desynchronized with one another. So take, for example, two devices simultaneously start a session, then they need to converge into which session they need to use. Or one of the devices, for example, might restore an old backup and end up sending a message using an old key that the other party cannot decrypt. And to handle these complex scenarios, Signal then introduced a session management layer, to be more precise, the Sesame algorithm, which is now responsible to manage for each partner, so potential partner, each of their devices, and how do they create, delete, and use the sessions within the messaging application. And at this point, then we had the question, does this additional layer, so this session management layer, still preserve the post-compromise security that we know that the single session Signal achieves? And to answer that question, we designed some experiments on the Signal app itself. To do that, we used some Android emulators to have two running devices where we installed from the Play Store the Signal application. Then we registered two honest users, and using this emulator, then we would perform the PCS attack. During our experiment, the threat model is slightly different, because here, while the victim is fully compromised, so the attacker knows the full state of the victim, we restrict it to follow the protocol, to strictly follow the protocol, meaning that it can only interact with the other parties by the user interface of the application. And while we were conducting these experiments, we actually discovered two violations of the post-compromise security, meaning there were two scenarios where the clone, even after a healing period, was not actually removed or locked out of the conversation. We will now look at one of those scenarios, and while I'll explain how we conducted the experiment, I will also introduce the features that made it possible to violate the PCS security. So we start our experiment by having two honest parties, so Alice and Bob. They exchange their messages normally. Then at some point, Alice's device is compromised, meaning that there is a clone device that the attacker has access to that has the exact copy of the state of the Signal application, meaning the attacker now has all secret key material of Alice. And at this point, then we put the clone device offline, and this allows then for Alice and Bob to exchange enough messages for their session to heal. And at this point, then there is a new feature of Signal that says that every 1 hour, sessions need to be reset between devices. So after 1 hour, then we have Alice and Bob that due to this time session reset, they completely remove the compromised session and they start a completely new session that the attacker doesn't know about. And what we expect at this point is that, okay, the compromised session now has healed, so it should be secure. And Alice and Bob at the moment are using a completely new session which has never been compromised. Therefore, the conversation should also be secure. So, and we try to test that. So to do that, we put online the device of the clone. And what happened is that due to this new feature, also Clone and Bob would reset their session due to the time session reset, meaning that at this point also now there is another parallel session between Clone and Bob that Alice doesn't know about. And the clone uses this session to send any new messages and receive messages from Bob. And we continued our experiment then by saying, okay, but what happens now if Alice goes back online? Like, is there some indication on the user interface that Bob cannot decrypt this message? Because now this old session, which we indicate by the square here, it is deprecated, meaning that Bob cannot decrypt this message. But again here, the Sesame algorithm says the following, that old session needs to be restored, and if there is any message being received from this old session, that session now needs to become the new active one. So in our scenario, what happened is that when Alice sent a message, Bob would then switch back to using the session that it had previously with Alice and continue the conversation in that session. And as you can guess, if the clone goes now again online and is sent a message, Bob will then think according to specification, I received a message from a deactivated session, I need to reactivate this one and still continue the conversation with the clone in this additional session. And as you can see this, Alice and the clone can continue into the conversation into two different sessions without the attacker or the clone ever being locked out of the conversation, or Alice having any indication on the user interface that there was something going wrong. And while we were looking at the specification and at the code, we noticed that there were several such interesting features of Signal that directly affect the security of the protocol. So we already saw that every hour there is a session reset. There, up to 40 sessions are stored per device, but here the policy on how do you delete this session between the specification and the implementation also do not match. There is the reactivation of old session, which is handled by the Sesame algorithm. Additionally, on the other second vulnerability, you could also have a retry feature, meaning if you cannot decrypt a message, you decide to reset the session one more time. And some other interesting parameters such as having the ability to store 25,000 forwarded message keys or storing 5 receiver and sending chains for each of the sessions. And while we were looking at the experiments of the results and also these features that Signal now has, then the question that we had was, then what is the guarantee that the end user is getting? Because obviously the one that is studied in the single session, it is not enough. And we also showed experimentally that security of this single session does not lead to the conversation of the user. And following this the experiments that we did, then we thought that maybe the guarantee that we really need to be talking about is at the user level. So at the conversation level, meaning that not only a single session, but we need to talk about X3DH plus double ratchet plus the Sesame algorithm, meaning multiple sessions of Signal. And that's exactly what we did. So using the Tamar Improver protocol verification tool, we did a formal verification of the session handling in Signal. So we started off by having a version of the single session Signal, so the double ratchet plus an abstracted version of the X3DH, where we could prove that PCS indeed held in this setting. And then in addition to it, we then added the Sesame layer, where Tamar now is able to refine the attack that we saw previously. So from the graph here, the 2 blue boxes are meant to represent that the attacker and the honest user can now have 2 distinct encrypt unrelated, independent conversation with the victim's partner. And since there was obviously a violation, that we also wanted to provide some fixes. And we proposed two solutions. So firstly, it was to disallow re-enabling old sessions. So for usability reasons, you could still store old sessions, but they should not be used to encrypt new messages. And in addition, we also proposed some clone detection mechanism, meaning that the victim then now should receive some warning message, and maybe something should pop up in their user interface that says that something is going wrong and someone tried to clone your device. And we, on the previous models that we have on the multiple sessions, we also added the fixes, and we were able to prove that PCS was indeed restored. And additionally, we could also prove the soundness of detection. And by soundness, we mean that if there was a flagged behavior in our model, then there was indeed a clone inside of the system. So there were no false positives. So to recap, we showed experimentally that PCS did not held at the user conversation level, but that not all is lost, and that the PCS can also be restored, and lifting this single session security at the multiple session that the end user gets. But maybe a takeaway from this talk is that Signal is just a first case study, because all other messengers also have a session handling layer. And maybe as a future work, we should start looking at the conversation level of the security properties inside of the secure messaging domain. Well, all technical work that we did here, so proofs and models, are made available, so feel free to check them out. And I'm happy to take any of your questions.